Let's try some more combinatorial questions. In this diagram, how many triangles, non-degenerate triangles, so triangles that are not in a line, how many non-degenerate triangles can be made by connecting 3 pink dots? So step 1 is to realize that permutation or order does not matter, so we're going to be using combination. Step 2 is to sort of look at this question, to strategize how to do this question. So instead of manually counting every triangle, we can do combinations. For example, we can select number of ways of choosing 2 points over here, and then the number of ways of choosing an additional point on somewhere else, plus the number of ways of choosing 2 points from this row, and then 1 more point from another row, or 2 points from this row and 1 more point from another row, or 1 point from each row. So we can strategize on how we can solve this. Another way we can solve this is by first finding all the number of ways we can choose 3 points, and then subtracting all the ways of choosing 3 points that do not form triangles, aka subtracting all the ways that 3 points are in a line. Let's assume that these are in a line. So we begin by counting the number of points. There are 10 points, and we choose 3 points, minus the total number of collinear, so points that are on the same line. So here we have 1 collinear point. Actually, let me change the color. So we have 1 collinear point. We have a second one. We have a third, well, a set of collinear points, sorry. We have 4. So minus 4, because 10 choose 3 includes these set of points, which definitely cannot make non-degenerate triangles. And how many other sets of 3 collinear points exist? Well, we have one over here. So we subtract 1 more. We have this set over here. Subtract 1 more. Yes, it looks a bit messy. Hopefully when you try to visualize this in your head, it's not as messy. And then how many sets of 3 points can be made from these 4 points? We have 4 points. How many sets of 3 points? That's 4 choose 3. And let's see, are there any other collinear points? Well, sets of collinear points, points on the same line, that could be made from these 10 points. It doesn't look like it, so this will be our final answer of the number of triangles that can be made from these points. 10 choose 3 minus 6 minus 4. Let's try another question. In a group, there are 5 men and 6 women. How many number of committees of 4 are there? So one way to do this is to specify the cases for each committee of 4. For example, case 1 can be that there are 4 men and then 0 women. Case 2 can be that there are 3 men and 1 woman. Case 3 could be 2 men and 2 women. Case 4 is 1 man, 3 women. And case 5 is 0 man, 4 women. And the sum of all these cases should give us a total number of committees of 4 that can be made from 5 men and 6 women. So how many ways are there of choosing 4 men from 5 men? There are 5 choose 4. How many ways are there of choosing 0 women from 6 women? Well, there are only one way of choosing that. Sorry, there is only one way. 3 men from 5 men, that's 5 choose 3. Choosing 1 woman is 6 choose 1. Notice that here we are multiplying because we're saying 3 women and 1 woman, so that's why we multiply. If this were 3 women or 1 woman, we would add them together. 2 women and 2 men, that's a total of 5 choose 2, 6 choose 2. Total ways of choosing 1 man with 3 women, 5 choose 1 times 6 choose 3. And total number of ways of choosing 0 men and 4 women, that is 5 choose 0 times 6 choose 4. So the total number of ways that we can make a committee of 4 from 5 men and 6 women is equal to the sum of all this. Or if we want to get fancy, we could write this as sigma notation. Let's say 5 choose I, 6 choose or I equals 0, 6 choose 4 minus I, all the way to I equals 4. And so this is the number of committees that can be made. And then you think, hold on a moment. If you're choosing 4 people from 5 men and 6 women, is that not just like choosing 4 people from 11 people? So shouldn't that just be 11 choose 4? And, we look at this and we say, yeah, it does make sense. And yes, it does make sense. So this is an example where we can split a question up into several cases, or we can go straight away to the answer. And so this is pretty neat. We have figured out not only how to solve this problem, but how to solve it in 2 ways. One using simple combinations, the other one using sigma notation. In fact, for the sigma notation, there's an identity like this. We could generalize this identity to Vandermonde's identity, which I will explain in another video. Thank you for watching.